All right. How do I share my screen? I think my screen is being shared. Okay, let's go ahead and get started with chapter 2. First of all, remember to download the student PowerPoint from Canvas. There are some blanks that you can fill in as we go along. Remember to download any handouts and bring them to class if you would like to write on them. Also, I'm aware that some people like to make vocabulary lists. So I've starred vocabulary words throughout the presentation, and you can go through and make yourself a list of those if you are one of those people. Here's a list of things we're going to talk about today. I want you to make special notes of the clicker questions because they are very important for the quiz, which you will be taking at the end. First, let's talk about chemicals. A chemical is any substance made up of matter. That means physically apparent stuff. So water is a chemical, carbohydrates, vitamins, minerals, all of these things are chemicals. Even organic fruits and vegetables have chemicals in them because they are made of chemicals. They are made of stuff. They are made of matter. Things that are not chemicals include light, heat, sound, magnetism, and gravity, basically forces. Let's talk about atoms and elements. First of all, the atom is the smallest unit of matter that still retains the properties of its element. But what does that even mean? Well, go ahead and watch this animation. You may have to watch it a couple of times to get all the answers, and go ahead and pause the video and do that. And then we're going to go on with some clicker questions. This is question number 1. What is the nucleus of an atom made of? Pause the video and answer. The answer is B. Number 2. The answer is A. Number 3. The answer is C. Number 4. The answer is D. Number 5. The answer is B. Let's talk about the structure of the atom. Nature is lazy and wants everything to be in the lowest energy state possible. And for atoms, that means a neutral charge overall, which means that the number of positive charges and the number of negative charges in an atom cancel each other out so that there's a neutral charge. The number of protons and electrons is equal. If the number of protons and electrons is not equal, that means that atom is called an ion, which is an atom with a positive or negative charge. And as you'll see here, an ion can refer to one atom or it can refer to multiple joined atoms. These are some common ions. Let me see if I can get my pointer to a pen. Here we go. Okay, so cut me some slack. I'm gonna have to use my finger to draw. Right here, we've got a, oh yeah, there we go. We have a hydrogen atom. The hydrogen ion, hydrogen with one positive charge, is the most common atom, and that is just a single proton without an electron. Over here, we have the hydroxide ion, which is an oxygen bonded to a hydrogen with one negative charge. That means one extra electron. Here's question number 6. And the answer to that is A. So this is the periodic table of the elements. I'm sure you've all seen it before. What we're going to talk about right now is these little numbers on top. These are what's called the atomic number, and that is the number of protons in the nucleus of each element. And that is what differentiates elements from one another. An element cannot be broken down into substances with the same properties. So if we were to take a bunch of gold, like a lump of gold, and break it in half, each half would still be gold. And if we break that in half, each half would still be gold, and so on and so forth. And the question is there a point at which it's no longer gold? And there is. So let's say that we have an atom of gold, which actually has quite a few protons, but let's just give it, I don't know, this many protons for the sake of the example. And we've got some electrons here as well. So once you get down to one atom of gold, if you try to split that any further, it is no longer gold. It is now something else. A great example here, we've got carbon. Carbon has 6 protons. 1, 2, 3, 4, 5, 6. If we take any of those protons away, that is, if we try and break down that carbon atom any further, it is no longer carbon, it is something else. And hydrogen is the most basic atom because it has only one proton. Oh, there we go. Well, the number of protons and, well, you can read that on your own. An atom has is called its atomic number. Carbon versus nitrogen. So carbon has 6 protons in its nucleus. So let's draw a carbon nucleus. 2, 3, 4, 5, 6. I'm just drawing the carbons, or the protons, sorry, and I'm going to draw the electrons. We're leaving the neutrons out of the equation because they do not matter to the identity of the element. If I add another proton, this is no longer carbon, it is now nitrogen. Nitrogen on its own is a gas. Carbon on its own is a solid. If I were to take away that proton, again, we have carbon. So if I were to add that back, we get nitrogen. And then if I were to add another one, we suddenly have oxygen. Oxygen is a gas as well, and it's what we breathe. And so on and so forth. Here is your question number 7. The correct answer here is C. Number 8, the answer is A. Here is the structure of an atom. I just wanted you to have this visually for when you're studying. We've got the protons and the neutrons in the nucleus, and then the electrons orbiting the nucleus in this sort of amorphous cloud, a shapeless cloud of sorts. These are the elements that you need to know for this class. They are the Schnapps elements. We have carbon, which is represented by the letter C, hydrogen, which is H, nitrogen is N, oxygen is O, phosphorus is P, and sulfur is S, Schnapps. These are the most commonly used elements in biology. We are going to skip this activity because this is an online class. All right, moving on. Chemical bonds. A chemical bond is a lasting attraction between two particles, any two particles. Chemical bonds between atoms are represented by lines like this. Well, there's a line. Oh, good Lord. You can see that. You can see the fucking lines. Anyway, and it could also be between entire molecules, as we see over here. We have one molecule and then there's another molecule, and they come together through a chemical bond to make a different kind of molecule. When atoms of 2 or more elements bond together in a fixed ratio, they have formed a compound. Compounds are also called molecules. This is an example of a compound right here. We have sodium chloride, 1 sodium atom, and 1 chlorine atom. The chemical formula of a chemical or a compound tells you the number and kind of each atom in a compound. So again, here we've got table salt. NaCl is the chemical formula. We have 1 sodium and 1 chlorine. Glucose, that's glucose right over there. Glucose is C6, meaning we have 6 carbons, 12 hydrogens, and 6 oxygens. So we say C6H12O6. The term organic refers to a compound that contains carbon. Organic is one of those words that can have multiple meanings. It doesn't just mean grown without pesticides. It also means a compound that contains carbon. And conversely, inorganic is a compound that does not contain carbon. So sodium chloride is an inorganic molecule, and glucose is an organic molecule. Here's a little activity we tend to do in the classroom. You can go ahead and do it if you want. I will give you the answers here. Let's see. I guess I can't really write the answers, but I can tell them to you. In sulfuric acid, we have 2 hydrogens. See, we've got our subscript 2. It refers to the letter before it. S, we've got 1 sulfur because there's no subscript, and we have 4 oxygens. Carbon monoxide, we have 1 carbon and 1 oxygen because there's no letter or no numbers after them. Beta carotene has 40 carbons and 56 hydrogens. And here is clicker question number 9. The correct answer here is B. This is beta carotene. I just thought it was pretty. You can buy this in capsules in the grocery store. It helps your eyes and stuff. It's just a really pretty molecule. Chemical bonds contain energy. And this is because electrons contain energy and bonds are interactions between electrons. Whenever a bond is broken, energy is released, and whenever a bond is formed, energy is consumed. This is ATP, adenosine triphosphate. That is the energy carrying currency of the cell. And we've got a really high energy bond right here between the last phosphorus molecule and the rest of the molecule. This bond right here is full of energy. So when that bond is broken, energy is released into the surrounding environment. If there's a process in the cell or a chemical reaction that needs energy, what the cell does is it grabs one of these passing ATP molecules and it snaps that bond, that third high energy bond, and then extracts that energy and uses it for the reaction. Here's clicker question number 10. The answer is B. Types of chemical bonds. We're going to draw a flow chart right now. Here is the flow chart. Chemical bonds. Wow, it's really hard to draw with my finger. We have ionic bonds that we're going to talk about. We're also going to talk about covalent bonds. Covalent bonds, there's two types. We have polar covalent bonds, we have non-polar covalent bonds, and one type of polar bond is a hydrogen bond. There we go, hydrogen. Let's talk about ionic bonds first. This is where atoms become ions throughout the bonding process. What ions, remember, ions are atoms with uneven numbers of protons and neutrons. That is, they have an overall positive or negative charge. This happens when atoms steal electrons from each other to get a full outer shell, meaning to get to that lowest energy state. This does result in ions. Here's our favorite ions. We have hydrogen and hydroxide. And if the attraction between the ions is strong enough to hold them together, it results in an ionic bond. Here's a diagram of sodium chloride. You see that there is an extra electron here that is stolen from the sodium by the chlorine. And then we have these two atoms, each is in its lowest energy state. Let's watch this animation. I really hope this works. No, play. Damn it. Okay, well, never mind. Covalent bonds. These are when atoms share electrons. The word co means together. There are two types of covalent bonds, polar and non-polar. In a polar bond, electrons are not shared equally, which makes the molecule polar. That is, one end is a negative pole, it's more negative, and the other end of the molecule is more positive. It is a positive pole. In a non-polar bond, electrons are shared evenly. That means their positive and negative charges are distributed evenly throughout the molecule. Here is a little animation about covalent bonds, which clearly is not going to work. Now I would have you do the handout properties of water, which you can print from the module. It's really helpful and I think you should do it, but obviously, you know, that's up to your discretion. Let's talk about polar covalent bonds. This is water. Water is a polar molecule. The oxygen side of the molecule, this side right here, is slightly negative. And the other side of the molecule with the hydrogens is slightly positive. Most molecules with oxygen are polar because oxygen is a very strong molecule. Oxygen and hydrogen in the water molecule are sharing electrons, but they are sharing them unevenly. Oxygen is very strong, and it is pulling those electrons closer to itself. So that gives the oxygen a slightly negative charge. It is not completely negative because it doesn't have too many electrons because it's sharing those electrons. It's just slightly negative. The total overall charge, however, is neutral. Non-polar bonds happen between carbon and hydrogen. Any molecule with only carbon and hydrogen is nonpolar. There are also other nonpolar bonds, but these are the ones that you're going to see most commonly in this class. Whoop. That means that there's no partial charge on any part of the molecule. The electrons are evenly distributed throughout the molecule. So I want you to see here, we have methane, CH4, that is a non-polar molecule. And then we have water, H2O, which is a polar molecule. Here is question number 11. Correct answer here is B, and you can tell because we have these red oxygen molecules here, and almost any molecule with oxygen is polar. Here's number 12. The correct answer here also is B, because we know that this molecule is polar. It must be the one with a slightly positive charge on one side and a slightly negative charge on the other side. Question number 13. The correct answer here is A, because we only have carbon and hydrogen in this molecule. And the answer to number 14 is also A. Number 15, you should pretty much know this by now. The answer is B. And number 16, the answer is A. Many atoms can make things polar, but we're going to focus mostly on oxygen here. Any molecule with only carbon and hydrogen is a non-polar molecule. Here are some important terms. Polar is synonymous with hydrophilic, which means that it loves water. It will mix with water. Non-polar is synonymous with hydrophobic, which means that it fears water. It will not mix with water. Here is clicker question number 17. The correct answer is B. Any molecule that can dissolve in water is polar because polar molecules like polar molecules. So over here we have water and alcohol, and you can see that those are polar molecules, so they will mix, and that is what allows us to have fantastic cocktails. Oil and water, on the other hand, do not mix. You can notice that oil is made exclusively of carbon and hydrogen atoms. That means it is non-polar, whereas water has oxygen in it, so it is polar. The polar and the non-polar do not mix. Soap is a very interesting molecule because it has a polar side and a non-polar side. So, you know, if you get your hands oily and you run them underwater and try to scrub off the oil, it doesn't work. That is because water does not mix with oil. However, if you use soap, the hydrophobic tail of the soap binds with the oil, and the hydrophilic part of the molecule binds with the water. And that interface allows the water to wash away the oil. This is a cartoon with a bear that says, "Help, help, I'm dissolving." The other bear says, "But bears are insoluble." And the first bear says, "That's easy for you to say, you're not polar." All right, let's talk about bonds. A hydrogen bond is a weak bond formed between a slightly positive hydrogen and any slightly negative atom. So in this case, we have a slightly positive hydrogen of water and a slightly negative oxygen of water. And this dotted line represents a weak hydrogen bond. Water can bond with other waters through hydrogen bonding. This is possible because water is polar, but that's not going to work. Click question number 18. The correct answer is D. Chemical reactions. Living things use energy through chemical reactions. I want to make very clear that chemical reactions is only interactions between atoms. Nothing is created, nothing is destroyed. Only rearrangement of atoms. The reactants are what we call the starting materials, so these are the reactants over here, and then the products are what we call the ending materials. They are the products of the reaction, and the arrow means that a reaction is happening. So let's go ahead and count up the number of atoms on the left. We have 4 hydrogens here and 2 oxygens here, and on the right in the products we still have 4 hydrogens and we still have 2 oxygens. They have just been rearranged. Nothing is created, nothing is destroyed. Here is number 19, and your correct answer to this one is C. Let's go ahead and do this exercise. The point of this is just to reinforce that nothing is created and nothing is destroyed in a chemical reaction, only taken apart and rearranged. This is just like cookies. In like when you're making cookies, you start out with flour, you start out with chocolate chips, you start out with eggs. You mix them and bake them, and that's the chemical reaction. And then in the end, you still have flour, chocolate chips, and sugar and eggs, but they are in a different shape, in different arrangement than they were in the beginning. It's exactly the same with the chemical reaction. So over here on the left side in the reactants, we have 1 carbon, and on the right side, we still have 1 carbon. We have 4 hydrogens in the left, and then we still have 4 hydrogens, 1, 2, 3, 4 on the right. We have 4 oxygens, and over here in the products, we still have 1, 2, 3, 4 oxygens. This is probably not going to work either. Metabolism, this is a vocabulary word. The sum of all the chemical reactions in an organism. Digestion, using energy, breaking down glucose and fats and proteins and starches, and that's how we use energy. Living things need activation energy to start their chemical reactions. A catalyst is something that speeds up a reaction. So activation energy, you can't just have a reaction occurring spontaneously without energy being put in to the reaction. Sort of like if you're lying in bed, you need to invest some energy in the act of getting up before you can do anything else. A catalyst speeds up a reaction by lowering the amount of energy required to start that reaction. For example, the reaction of dissolving sugar. If you put some sugar in some water, well, that's not going to dissolve very quickly. It will dissolve eventually, but if you add heat, it will dissolve much more quickly. Now, that's an example of a chemical reaction in which heat is the catalyst. Heat has provided extra energy for the reaction to start. Enzymes are proteins that are catalysts. If you add them to chemical reactions, they will speed the reaction up. This is an example of a combustion reaction. Heat is the catalyst here. You have natural gas, methane, and we have some oxygen. And if you add them together with the catalyst of heat, then you get carbon dioxide and water. An enzyme is a molecule that acts as a catalyst. Generally speaking, it's a protein. A good example, analogy for this would be scissors. Scissors, what they do, they cut paper, they cut things. They participate in that process, but they're not permanently changed. They can be returned to their original state and used over and over again. An enzyme is exactly like that. Go ahead and watch this animation and come back and answer the clicker question, number 20. The correct answer here is D. 21, also D. A chemical reaction will consume energy or it will release energy. Whenever a bond is broken, energy is released, and when a bond is formed, energy is consumed. So again, we have our favorite molecule, ATP, the energy carrying molecule of the cell. We've got this high energy bond right here. And when that bond is broken, energy is released into the surrounding environment. And when it is put back together, when the bond is formed, energy is consumed. Energy is put into that bond. You can think of a bond as like a chemical bond, as like a container of energy. When you open it, when you break it, the energy is released. And when you package it up, when you close it up, when you make it, then the energy is consumed. The energy is stored in that package. Let's talk a little bit about water and how its life-supporting properties come to be through its polarity. These are all because of hydrogen bonds and all because water is polar. Cohesion, adhesion, surface tension, ability to moderate temperature, evaporative cooling, great solvency, and the fact that ice floats. All of these make life necessary or make life possible as we know it. Let's talk about cohesion and adhesion. Cohesion is the tendency of molecules of the same kind to stick together. So right here, we've got water molecules sticking together. That's called cohesion. Then we have the tendency of water molecules to stick to things other than themselves, like this. The water is attached to the cell wall. That's called adhesion. Both of these are possible because water is polar and creates hydrogen bonds. Capillary action is the action of water rising through narrow tubes. So you know when you take like a corner of a paper towel and you dip it in some water, and the water climbs up through the paper towel, that is because the water, well, this isn't going to work, but that's because the water is climbing up through the tiny little tubes, the fibers that make that paper towel. It is using cohesion and adhesion, and that is capillary action. This is actually a really good animation. I'm sad that it's not going to work. It shows how water uses these capillary tubes and capillary action through cohesion and adhesion to rise all the way up to the very top of trees. Development of these tiny little tubes called vascular tissue, that was necessary that was an evolutionary development necessary for trees and other plants to grow tall. Plants without these things have to stay low to the ground, like mosses and lichens. Cohesion is related to surface tension. Surface tension is just a measure of how difficult it is to break the surface of a liquid. Here we have a little water strider bug. You can see that it's resting on the surface of the water because the weight of the bug is not great enough to break the surface of that liquid. You can see the little dents. That's because all of the water molecules are hydrogen bonding to one another, forming a surface that the bug is able to stand upon. This is a really cool animation. It's a video from the International Space Station of what happens to water in space. You should watch that. It's very cool. Water is actually able to moderate temperature. As water evaporates, it cools. It takes heat with it. That's called evaporative cooling. And this is why when you rub your hands with, what's that stuff called? Hand sanitizer, yes. You rub your hands with hand sanitizer, your hands begin to feel cool. That's because water is evaporating. It's coming off the surface of your hands, taking the heat with it. And this is also how sweating works. Solid water is less dense than liquid water because of hydrogen bonding. So here we have some water in its liquid form. Notice the hydrogen bonds are keeping the water molecules pretty close together, but when those hydrogen bonds stabilize through freezing, when they become solid and stable, they hold the water molecules farther apart than they would when they were liquid. And this is really, really important because it means ice floats. Imagine if there were a lake or a pond with some fish in it and some plants and stuff, and winter comes, the surface of the lake freezes over and the ice floats. That allows the plants and the fish to continue living throughout the winter. Imagine if water did not float. If water molecules were not polar, then ice would not be less dense than liquid water. That layer of ice that forms on top would fall to the bottom of the lake, squashing the fish, squashing the plants and everything that's in there. Then the top layer of the water freezes again, and that next layer of ice falls to the bottom of the lake until the entire lake is solid ice. All of that is all of that is not possible, thank God, because water is polar. Water is a great solvent. That means that it can dissolve things very well. In this picture right here, we've got some salt water. The salt, the sodium, and the chlorine are being pulled apart from one another by the polar nature of the water molecules. An aqueous solution is one in which water is the stuff that is dissolving whatever solid you put in it. So salt water is an aqueous solution. Vodka is also an aqueous solution because you've got vodka in the water. All right, let's talk about acids and bases. This is the pH scale. The pH scale just tells you how acidic or basic something is depending on the relative number of free hydrogen and hydroxide ions. Remember, those are our favorite ions in biology. In a solution, it goes from 0, which is very acidic, to 14, which is very basic. 7 is neutral, and pure water is the only thing that is exactly neutral. A buffer is anything that stabilizes the pH of solution. We will be working with some buffers in class later on. Time to draw. Okay, let's see if I can do this with my finger. So we're going to draw the pH scale. Down here is pH of 0. And up here is pH of 14. Now you've got to be careful because you would think that bases are at the base of the scale, but they're not. Bases are at the top. The most basic things have a pH of 14. And in bases, the number of free hydroxide ions is greater than the number of free hydrogen ions. That's supposed to be a little plus. Ugh. Well, whatever. Down here at the bottom, this is acidic stuff. Acids have a greater concentration of free hydrogen ions than hydroxide ions. And right here at 7, that's neutral. That's where the number of hydrogen ions is equal to the number of hydroxide ions. There we go. So in an acid, we have a lot of hydrogen ions. Concentration of hydrogen ions is higher at the bottom than at the top. And in a base, the concentration of hydroxide ions, it's supposed to say OH minus, is higher at the top than at the bottom. So it's an inverse relationship between the concentration of the hydrogen ions and the hydroxide ions. Here's some more facts about acids and bases. Acids take hydrogen from other particles. Please watch this animation. Hi. Bases give hydrogen to other particles. Can you close that door, please? Go ahead and watch this animation, please. And neutral items, oh, there we go, such as pure water, can donate and receive ions equally. So this is an animation showing you how water can be an acid and a base as well. Go ahead and watch that. There's a picture for you. This water is a base over here on the left, and this water is acting as an acid because the acid is giving away its hydrogen to the base. That's for you to study with. Here's our final clicker question. The correct answer is ... A. Okay. We're going to skip this part. And this is a concept chart that you can do on your own if you so desire. I want to keep my ink annotations. No, I don't. All right, go ahead and take the quiz. That is all. I hope you have a lovely day. How do I stop this? Stop sharing. No. Record. Stop recording.